This session and the next are the last two sessions of this very long chapter, the longest in the book, 22 pages of a text of about 150. I'll probably go over 50 video clips for this chapter, which is not surprising, but it's a very important chapter, a lot of theory, gives you the real basis for understanding principles of quantum mechanics. This one and the next one. Chapter 7 will be on angular momentum and spin and so forth. Also a lot of theory. Right? So last session we derived that if you differentiate the expectation value of some observables operator, A hat, so the observable A, whatever it is, you differentiate it with respect to time, you'll get this expression, so 1 over h bar and the expectation of the commutator. And the commutator is of the Hamiltonian operator, or the energy operator, all the same thing, usually just shortened to Hamiltonian, and the A hat, the operator corresponding to the observable A that you're talking about. Okay? So now the question gets asked, when, under what circumstances does A commute with H? In other words, the commutator is 0. So when does that happen? What properties does A have to have for this commutator to be 0? And of course, if the commutator is 0, then this expectation value, the average value, is stationary, meaning it's conserved. It does not change with time. It remains constant. So if you differentiate a constant, you get nothing. Right? Okay. Well, here's an example of the type of property that A needs so that it does commute with H. Now here's your H, your Hamiltonian, your energy operator, H hat. So it's just the kinetic energy and plus the potential energy. When you, or if you decide to do a master's level M1 course with me on classical mechanics, you'll be very familiar with this Hamiltonian from classical mechanics, the classical Hamiltonian, which is the kinetic energy plus the potential energy. So quantum mechanics takes over a lot of the aspects of classical mechanics, especially the Hamiltonian and something similar to the Hamiltonian called the Lagrangian. And quantum field theory is just full of Lagrangians. You write out your Lagrangian for the quantum mechanical system that you're talking about, and then you start doing the mathematics. So the Lagrangian is basic. That's jumping ahead a whole course. Okay. Well, as an example of when A, under what circumstances does A commute with H, so that the commutator is 0? Well, here's an example. So take your potential here, and imagine it's a function of r, the vector r, just the position, and assume that this potential here does not depend on x, on the x component of the position. So it depends only on y and z, let's say. Okay, so the v is a function only of y and z. Now px, the x component of the momentum hat, so the operator, it commutes with p squared. Is that obvious? Because p hat squared is px squared, hat, py squared plus pz squared. That should be fairly obvious to you. So px commutes with this. Okay, it also commutes with y hat and z hat, right? And therefore, implies the x component of the momentum hat, as an operator, commutes with h. Okay. Because what is h? Well, it's this. So this px commutes with all these, and v does not depend on x. Okay. Therefore, px commutes with v. So if it's commuting with all these terms and v, it also commutes with h, right? So therefore, the p, the x component of momentum, hat as an operator, that operator therefore commutes with h naught. H hat, and therefore this is 0, and therefore the expectation value, the average value if you measured p of x, px, would be constant, right? So this is px gets conserved because of this result here. So that gives us an answer. So so you can say in a sense that because v is independent of x, then that it's that independence that gives you that px gets conserved. In other words, if you differentiate it with respect to time is 0, because the average value, the expectation value, same thing, is constant. Okay, so so conservation of the x component of momentum. That links with symmetry. So where's the symmetry here? Well, if you, because this the Hamiltonian is independent of x, so if you move the system along the x-axis, it won't make any difference to the system. Right? All the physics remains the same. And so you can say that the system is in the sense you can move it along the x-axis and nothing changes. So in a sense that system then is symmetric under translation. You're just moving it along the x-axis in the x direction. Okay, so there's your symmetry in a sense. So here's your system, whatever it is. Here's the x-axis, and you just move it some distance along the x-axis. Doesn't change anything. So there's a kind of symmetry in that sense, right? And we'll do something similar in quantum field theory at M1, first year master's level, when we talk about quantum field theory and Noether. We talked about a bit before Emmy Noether's famous the Noether theorem, which says I'll just give you. I'll throw it at you. I'll give you a bit of a taste of what's coming. A year higher, first year masters, quantum mechanics, quantum field theory, is your Lagrangian. Think of a Lagrangian, somewhat similar to a Hamiltonian. They're related. So if there's a symmetry in the Lagrangian, there will be a corresponding conservation theorem. Conservation of something, some physical quantity gets conserved. So here was an example where the x component of the momentum got conserved. It remains constant. So if you differentiate with respect to, anything, if you differentiate with respect to time, you get 0. Okay, so this idea of this link, this intimate link between symmetry of your physical system, some kind of symmetry, and corresponding to that symmetry will be some equivalent conservation law. Something gets conserved. Some physical thing, whatever it is, will be conserved, and the two are closely linked. So this kind of idea, symmetry, hence a conservation law. Something gets conserved. That idea exists in both quantum mechanics and CM, that's classical mechanics. So it's a pretty deep idea and exists in both. All right. Now, this square here, nothing really new. We're heading towards a kind of summary now. We're sort of wrapping things up in a long. It really will go over 50 video clips for this chapter. Long chapter. All right. So it's effectively revision. So if you have operators, they're said to be compatible if they commute. Right. So in other words, the commutator of two of those observables, if that commutator, well, so say observables A and B with corresponding operators A hat and B hat. So the commutator you're written with square brackets, a hat, comma, b hat is defined as a hat, b hat minus b hat, a hat. If that commutator is 0, then the two operators, a hat, b hat, are said to commute. Right? And those two observables, a and b, are called compatible.